On the 13th of July, 1976, this spillway of the giant Mica Dam underwent its final tests with the release of reservoir water down into the Columbia Canyon. A display of the tremendous power of a river before that energy would finally be turned to profit. This test signaled the readiness of other phases of the project too. The reservoir, now known as Kinbasket Lake, had reached its working level. A 215-kilometer-long watercourse destined to become a source of electrical power. The dam controlling these waters was completed, and deep in the rock of the west abutment, a power plant would soon be ready to produce first power. On October 13, 1977, 1,000 guests assembled in the Powerhouse to witness the inauguration of service. But new power was only one of the achievements being celebrated on this day, for the Mica project was the key in long-term negotiations between the U.S. and Canada to stabilize the devastating flow of the Columbia River. Although negotiations relating to the Columbia had encompassed the previous quarter century, actual development started in 1964, following ratifying of the Columbia River Treaty between the United States and Canada. Both nations were to share in the benefits. The treaty called for the construction of 3 dams in the Columbia system in BC. One at the head of Kootenai Lake to control the flow on the Duncan River. Another on the main stream of the Columbia to convert the Arrow Lakes into a reservoir. And the third, a dam at Mica to control the headwaters of the Columbia in a reservoir now called Kinbasket Lake. The British Columbia Hydro and Power Authority was assigned the responsibility of building these dams and lost no time in getting the project underway. Engineers moved quickly to transpose requirements of the treaty into construction details. The United States would benefit through control of downstream flooding that in one single year left 38,000 Americans homeless, and would also obtain significant amounts of extra energy from 11 power dams located on the Columbia in the U.S. Americans had much to gain through flood control. Canadians, too, had faced their own flood problems over the years, and many were counting heavily on regulation of the river. Over the years, they had sustained losses in the millions through damage to communities and to farms and livestock along its course. But Canadians were counting just as heavily on the power potential of the river. The Mica development alone would mean 2.6 million kilowatts. 2.6 million kilowatts of clean electrical energy from the abundant snows of British Columbia's mountain ranges, and make possible a further power development downstream in the province. Time was a factor in the treaty agreement, and the hydro contractors lost no time in getting on with the project. The Duncan Dam, built for storage and not a power dam, was completed first. 6 months ahead of schedule, it started to store the sporadic flow of the Duncan River in a new reservoir. By regulating this tributary storage in accordance with the treaty, this dam had its effect on the volume of the downstream Columbia. Incidentally, in spite of the upset of construction, the valley remains unchanged in many ways. The next project at the lower end of the Arrow Lakes, known as the Hydro Keenleyside Dam, was completed in October 1968. This, too, was developed as a storage dam to partially regulate the flow of the Columbia between Castlegar and the 49th parallel, where flooding was almost an annual occurrence. It's equipped with locks to facilitate the movement of log booms and other river traffic. and control gates to regulate the outflow of waters. The control of this section of the river was not achieved without sacrifice. Many residents in the reservoir area were called upon to give up their traditional routes to the rising waters. Many farms, several villages involving a total of about 2,000 people had to be relocated. What could be done to offset such losses was done. New waterfronts, entire new villages, new roads, new beaches, and picnic grounds were developed. And efforts are continuing to make the Arrow Reservoir as compatible as possible with the living need of its residents. But full adjustment will take time. We come now to Mica, in the Big Bend country north of Revelstoke. This was the scene facing engineers in their contemplation of the project. Down in the foreground, the proposed location of the dam. And here, in artist's perspective, we see the reservoir, the dam, and a cutaway view of the underground powerhouse designed to produce the electrical energy. Except for the narrow line of the old highway and a network of logging trails, this was virtually the same wilderness that faced the fur brigades of 100 years ago. A lonely monument to the memory of their historic boat encampment was located almost on the site of the new dam. Upstream of this lay the future reservoir, with its tributary arms, the valleys of the Canoe and Wood rivers. The new lake to form here would be 215 kilometers in length and would store the seasonal runoffs from 4 mountain ranges, the Selkirks, the Monachees, the Purcells, and the spectacular mass of the Rockies themselves, including the Columbia ice fields. Here in the rock-bound wilderness lay the challenge. Here, straddling the backbone of North America, rested the latent energy of the project. 145 kilometers of heavy-duty highway, capable of 200-ton loads, were built to parallel the river, following the route of the old highway to the construction site. Between 1,000 and 2,000 workers would live in construction quarters in the area. And Mica Village, where some would bring their families to live for periods of up to 9 years, was built to meet their domestic needs. Hard rock miners were among the first residents. They started driving twin tunnels through the rock of the east abutment to divert the river around the site of the new dam. Each tunnel 900 meters long and 14 meters in diameter. Over 2 years were required to divert the river, but the tunnels had to be lined with concrete and provided with intake and outlet portals to control the flow. But tunnel crews did their works well, and the dam builders were now able to start the major operation. Protected by both upstream and downstream cofferdams, a small army of men and machines battled to excavate the old river course of glacial debris. Out of this pit, here seen nearly 60 meters below river level, millions of tons of sand, gravel, and glacial till were being removed. Engineers were taking no chances. They were providing a foundation of solid rock grouted in the most critical areas. Based on 800 meters of river bottom, they were preparing to build a structure 240 meters high, using rock and gravel laid in careful formation around an impervious core of glacial till, destined to be one of the highest earth-filled dams in the world. After about a year of removing unwanted materials from the riverbed, foundations were consolidated, and the actual building of the dam was underway. Battalions of dumpers, the largest of their kind at the time, were laying the fill. On the walls of the canyon, crews cleaned and grouted the rock of the abutments where the dam would finally make contact. Borrow pits, 5 kilometers upstream where the materials of the dam were obtained, became a scene of endless activity that went on year after year. In this, an important consideration was winter. 1.5 meters of snow fall by the end of November. And beyond that, it can increase to almost 5 meters by February. For several winter months, the project had to go underground or undercover. One operation took place in what was whimsically called the greenhouse, a plastic canopy heated inside so that concrete to seal crevices of the abutment walls could be poured in freezing temperatures without endangering its setting requirements. In freezing weather, this was one of the better places to work. For those who didn't have to work, winter wasn't all that bad. Any youngster who went through the Mica years would likely agree. The reservoir area was another challenge. Hydro had undertaken to clear the entire floodline of forest growth along nearly 480 kilometers of valley walls. Logging contractors took on the job of clearing and of salvaging marketable timber. Literally thousands of loads of timber were salvaged and trucked to the mills downriver. And with the passing of time, from the air one could see the progress of the clearing along the valley walls. Clearing was in itself a tremendous undertaking for both the BC Forest Service and the logging contractors. And they knew that an equally big chore lay ahead, for later when the reservoir started to fill, slash from the forest operations would rise on the waters and have to be disposed of. A reservoir of such vast dimensions would eventually float up a lot of debris. That was still to come. As the structure of the dam slowly rose out of the riverbed, another group of hard rock men moved in to blast the root of the Spillway channel in the rock of the east abutment. Rock-bound channel, one of the safety features of the dam, was designed to lower the reservoir in the unlikely event that it ever exceeded its maximum water level. After excavation, lining it required 47,000 cubic meters of concrete. And later on, across the valley in the west abutment, other hard rock crews had blasted the contours of the intake structure. These were the ports through which the water would enter the penstocks leading down to the Powerhouse turbines. A spectacular time for visitors. Thousands year after year made the trip from Revelstoke to watch the progress as zones of the fill gradually built up around the impervious gray core of the structure. By June of 1972, after 4 years of placing the fill, the dam was nearing completion. Only a few more months to reach the final crest line. The endless roar of machines continued. As the dam neared completion, hard rock men had driven access into the mountain rock of the west abutment. Tunnels and shafts ranging in diameter from 3 to 18 meters gave way to the drills of the miners. These were the caverns of the generating system that would turn the latent energy of reservoir waters into electrical power. Well over 1 million cubic meters of rock were blasted to make room for penstocks, elevators and power conductors, for ventilation, for transformers, and for tail race waters, not to mention the cavern of the Powerhouse itself. Higher than a 12-story building and longer than a city block, but this was only the beginning. Thousands of tons of concrete and steel would be used to turn this into a powerhouse. Contractors were going all out, not only to meet the terms of the treaty, but also because British Columbians would need new power. On the upstream side of the dam, the intake structure was now completed, and the waters of the reservoir were rising according to plan. The storage and use of water was what the project was all about, and this reservoir represented the new energy. It now confronted the forestry people with the disposal problem of hundreds of hectares of floating debris. A big challenge, and one that would require years to complete. Meanwhile, the endless parade of dumpers continued. They had reached the crest line. 32 million cubic meters of fill lay beneath their wheels. The end was in sight. This mammoth structure to control the headwaters of the Columbia was declared operational on March 29, 1973. Canadians had fulfilled the terms of the treaty in harnessing the river, and they had done it on schedule. Meanwhile, as sections of the underground structure were completed, mechanical and electrical crews pushed on with the installation of power generation equipment. The need for new power in BC was very real. Massive scroll casings to direct the waters of the penstock into the turbine runners. Steelmen, electrical crews, concrete contractors combined their skills to set the massive components in place. 4 turbine generators were scheduled to be online in 1977. 2 more would follow later, as and when required to meet demands. The 6 of these machines, among the largest in the world, would have a total output capacity of 2.6 million kilowatts of electrical energy. Here we see the runner and shaft of one of the turbines moving into place. This was the impeller and shaft that would convert the high-pressure flow of waters into mechanical motion and drive the electrical generator that would be mounted on its upper end. A ponderous load, 290 tons of steel moving down with delicate precision into the turbine pit. This was the crucial time when component parts manufactured by a variety of suppliers all came together to form the functioning assembly of a turbine generator. The runner had now reached its final position opposite the valve ports that control the water intake. The time for power was near. Since 1973, the reservoir had been storing the runoff of the glaciers and monitoring their rampant discharge through ports in the base of the dam. Now, that wasting energy was about to be diverted through the power machinery. On October 13, 1977, in the Great Vault of the Powerhouse, after honored guests and officials had spoken, the Honorable W.R. Bennett, Premier of British Columbia, threw the vital switch. A flashing globe signaled the start of the giant machines. Excitement grew as the speed increased to a point when a second flashing globe indicated that generators had reached their operational RPM. The machines were now in cycle with the provincial power grid and ready to be switched into service. And the climax came when a third globe flashed the signal that the new energy was online. The Mica project, having already started regulating the downstream waters of the river, was now serving British Columbians with electrical energy. Today, the Mica project serves in tribute to the vision, courage, and the stamina of those who foresaw its need and made it possible.